now discuss consistency. You might have expected us to discuss consistency first. Remember that a system is consistent if it has solutions. So ideally, you think you decide whether a system is consistent first before you start looking for solutions that might not exist. In practice, not really. You try to solve the system using Gaussian elimination, and if things break, then there was never a solution to find. Theorem. A system is consistent if and only if its last column is not a pivot column. That is, after you put its augmented matrix into row echelon form, there are no rows that have a single non-zero entry in their final column. Why does having a row like that mean you don't have solutions? Remember that each column represents a variable, except the last one, which corresponds to an equality. And this row represents an equation, 0x1 plus 0x2 plus 0x3 plus 0xn equals C, which is not equal to 0. But this is just 0. So 0 equals a non-zero number. That's a contradiction. Clearly, there's no way to make that equation true. And so there are no solutions. You need to put the matrix into row echelon form before you use this theorem. Consider the inconsistent system x plus y equals 1, x plus y equals 2. This is clearly inconsistent because x plus y is being set to two different things. The augmented matrix of the system is 1, 1, 1, 1, 1, 2. And it does not have any rows that look like this. However, the first step of Gaussian elimination will be to multiply the first row by -1 and add it to the second row, giving 1, 1, 1, 0, 0, 1. And now that this is in row echelon form, you see a row with this form, confirming that no solutions exist. Unfortunately, as we sort of mentioned earlier, this doesn't really save us a lot of time if we are going into problems without already knowing whether a solution exists. So suppose we have a system that we want to solve. We'll use Gauss-Jordan elimination. We'll store the system as an augmented matrix and perform the forward phase to put it into row echelon form. And then the backward phase to put it in reduced row echelon form. And that's the solution process. Well, once we've performed the forward phase, we can see if there are no solutions and stop working. But performing the forward phase was the slow part of the algorithm by an order of magnitude. We've basically done all the work. So knowing not to bother to perform the backward phase isn't saving us a lot of time. Furthermore, in most applied situations, I think you go into it knowing whether the system is consistent. So the results of this video are more theoretical than practical, but it's a very important theorem. We'll use it throughout the course. In this video, we have seen how to determine the consistency or inconsistency of a system by putting its augmented matrix into row echelon form.